My name's Nick Lavery, and I'm from Swansea University, and I was going to introduce the rest of my team, but they're not here, so don't worry about them, we'll move on. But the whole additive research that we're doing down at Swansea does depend very much on having a team. Without them, in fact, speak of the devils, there they come. So yeah, there's Stuart Shah and Professor Steve Brown and Mark, and we've all come up from Swansea too. We've been working on the AMAZE project for quite a while. We've covered quite a lot of different areas within AMAZE. So the main thing that we came in onto AMAZE was to work on the computational modeling of the process, which was something which Steve and I got a background in casting, so we like melting and solidification and the modeling of that kind of stuff. So we were very interested in that. But we ended up buying a ALM machine, so we got into builds, and then of course we do a lot of mechanical and properties, so we're also doing property measurements, and we also done some life cycle analysis. But what I'm going to concentrate on here is talking about the computational modeling. We've looked at it from quite a few different length scales, right down to what we call the powder model, and we've used a variety of different modeling techniques. LBM is lattice Boltzmann, so Steve's programmer at heart, and he developed a lattice Boltzmann model. I'll show you some of the results from that. I prefer to use commercial codes. I've been using Fluent for a while, so I did something in Fluent and MATLAB. We've also got Mark sat at the back there. Mark and Steve worked on a discrete element model, which I'll also show you a few little results. Not going to talk about all of these. We did a lot of that throughout the project, so it's kind of we're just going to talk more about the hatch scale model, which is in the middle there, which covers the sort of millimeters to tens of millimeters, basically on the scale of hatch patterns. I am trying to show as much as I can more recent results. So this is the type of modeling that you can do in Fluent. And what we're looking at here is, if you look at the top right-hand corner, you can see the scale of the simulation. You've got a laser beam coming down, and in this case, we're actually treating the powder as a continuum, and you can see the evolution of the bead, the free surface. This is just a 2D model because it allows us to look at this. There's a couple of variations here. So one is we just assume that we have the laser coming down and that you've got like a solid body. It actually reflects some of the laser energy away. But then the other model, so this one here, assumes that the powder actually does have an optical penetration depth. So this is something which I'm going to come back to more because we're going to need to use that in the new hatch model that we're working on. So what we've got here is this is the model which Professor Steve Brown developed towards the beginning of the AMAZE project. And it's a lattice Boltzmann model. You can see a laser coming along. Now, what I haven't got here is some videos of this process up and close. They're quite difficult to get hold of. But this is actually looking very similar to what happens in reality. And that's the discrete element model, which was developed at Swansea and has now been integrated into ESI's code. And it allows you to individually track the movement of particles as they get deposited by the wiper. So these are all that's some of the background modeling that we've done before. So what I said I was going to concentrate on now was on this very simple thermal model that we developed. It's a three-dimensional thermal model. With a powder layer, it can vary, a substrate. And to start off with, we're just going to be looking at some of the simulations. Now, it doesn't do the top part of the bead. So it's a very simple model. It just does the penetration depth, okay? So this is kind of very standard in welding, where you're not looking to get the top part of the bead, but it's almost going back to the analytical solution. So it's only one step above analytical. And the idea was that we want to have something very pragmatic, very fast, that we can look not just at single lines, but then eventually be able to do many lines, a hatch pattern, and then build layers, and eventually, hopefully, get to be able to do complete parts and get the thermal history. And in doing so, hopefully give us some better understanding of the interaction between the laser and how the weld itself is developing. So what we saw previously was a conductive mode weld. So this has now gone into what is a transition into a keyhole mode, depending on the energy density. These are the model results. So all models should be validated, without a doubt. And the whole purpose of this rather simple model was that we trying to get it validated. So paper by Bertoli from actually this year shows the kind of experiments, single laser tracks, different powers, increasing powers, and different line speeds. So it's just varying power and speed. And you can see the breakup of the droplets. You can see some continuous tracks, and you get breakups, which are due to the ready plateau instabilities, where the surface tension forces are weaker than the viscous forces, and it can't hold it together, and it breaks up into droplets. So the good thing about that paper is that they've done all the measurements, they've cross-sectioned it, they've got the depth of the melt, they've got the width of the melt, and we can then compare it to our models. And they're not spot on, but the trends are being followed. And we think that is quite a good start, because it's a simple model. It means we have less parameters that we're assuming, less fudge factors. We can play with one. And at the moment, we know where it is that we're going wrong, and we're trying to improve it. You can see within the error bars, so this is on the width. Within the error bars, we're actually not too far off, depending on where you are. So, but again, the trends are followed. So you've got large penetration where you've got keyholing happening, and then when you've got conductive mode welds, you have a smaller weld depth, and that trend is followed. So something is going right in the model. And the other thing you can do with these kind of simple models, you can use an empirical equation. So this is the Plateau-Rayleigh instability criteria, which says that pi times the diameter of the bead divided by the length of the melt pool has to be greater than 1 in order to have a continuous melt track. So, Russians have been working on this, Bisarov and Smurov. They say that for powders, that criterion has to be modified slightly, and you have pi over d over L. Pi d over L is greater than square root of 2 over 3. So what we can do is, because we're predicting what the length of the melt pool is, we know what the width and the depth are, what we can do is we can work out whether or not we satisfy this criteria and how it compares to the experimental. You can see this continuous length here, it only really happens for these dot 3 here with the lower velocity and the lower power. So you see continuous length, and all the rest are nosed. The red ones here are basically nosed. These are possibly, and the green ones are yeses. So that simple model with that simple criteria is matching what we're seeing in the experiment. Now, another way to look at what's happening here is, this is published data by Americans from Lawrence Livermore, called Wayne King. And you can see these are conductive mode. So we've got, this is a normalized enthalpy. It's just an index of the energy density of the laser. This is the normalized depth of the melt pool by the depth divided by the beam width. And you can see you've got conductive mode and the lower energy densities, the normalized energy densities, and then you've got keyhole happening further up. And and this is very similar. You look at the scales, around about a normalized enthalpy about 30, normalized enthalpy about 30, similar sort of depth to beam width ratios, and we predict conductive and then keyhole mode welding going on up there. So we're getting quite similar trends again, even on other papers. But it's that prediction of the transition. All of that was for continuous lasers. So the machines that we've got, Renishaw, work with modulated lasers series of spots. But for the model, it makes no difference. You can just switch on the laser switch off or continuously. It's very, very simple. But again, we can see this conductive to keyhole transition in the model. What we do have, which is takes this model and makes it a little bit more special, is that we can measure thermal diffusivities and thermal conductivities of the powders. So we're using some of the equipment we have, laser flash analysis, to get thermal conductivities. And you can see, the very low thermal conductivities, but they do make a difference. There are differences between different powders and different size fractions of powders. These are our own experiments now on the machine, similar sort of setup. We've got a plate. This is a cross section. I don't think I've got any pictures of the top part, but you can certainly see. So here we vary the power and the speed, and you can see that sometimes when you've got the higher energy density, you can see that keyhole, and you can sort of see transitions. And so we're still trying to. There's a lot of data to extract from that. We only did this a couple of weeks ago, so it's very recent. When we compare a model with the orange lines here are the data points that we have taken out from those lines at the moment. And you can see actually that in terms of the depth of penetration, we're actually almost even closer than with the continuous data, because it's our own. But we're a bit off with the widths at the moment. But again, the trends are followed, and we think that when we get more of those lines analyzed later on, we'll be able to have hopefully a lot more points and work out why exactly is where the variations are in the model. So when we do a sensitivity study on the model, looking at different thermal conductivities, it's all behaving quite as you'd expect. So if we take the thermal conductivity of the powder down, the depth goes down, it's insulating it more. So it's not massively, it's not illogical by any means. The variation on the width is slightly different. There's a lot of things we don't have in this model. We've kept it simple. It's only a thermal model. It doesn't have Marangoni, it doesn't have fluid flow. We know those influence it, but we're trying to stay away from that because that's what adds the overhead to running the model. So the whole idea of this is for it to be pragmatic. Again, another thing you can change is the bed thickness. And again, the trends go in the right direction. So if we have a thick bed, the penetration goes down. And if as the layer thickness goes up, also the weld width goes up. So those kind of logical sensitivity studies on a model that show that it does make sense physically and it's quite easy to justify. What we're trying to get to eventually is the idea that we can do some measurements of properties, and in conjunction with the model, we can simulate process maps. And this is going to be handy because optimization experiments of the machine can take quite a long time, and it's a lot of trial and error. So if we can get there by a few fast measurements, but even better than that, sometimes when we're going up to higher power lasers, we're not quite sure. It's not necessarily a linear relationship between you double up the power of your laser, it doesn't mean you can automatically double the speed. There's not a linear relationship, and that relationship, this will help us try to find that relationship so we can find the fine-tuning point where we can avoid the keyholing, because in general we want to avoid keyholing and stay away from it. We need to improve the model, so the way we assumed that the penetration of the laser through the powder was not obvious to us at the beginning, that's become more obvious now. The Russians already knew it a while back, and so they've got some equations that suggest how you can actually, in titanium 6-4, the penetration of the laser of an optical laser like this into a powder bed is of the order of the powder bed thickness. So it can't be ignored. You can't just assume you've got a heat source on the top. So that's it, really. It's a simplified physics model. It's pragmatic. Hopefully it's going to take us to be able to rapidly predict process maps, but potentially build entire components eventually where we can have the thermal histories in some form or another. So it's not massively precise, but it might allow us to do maybe thermal histories plus residual stress in a pragmatic way where we can look at the entire component eventually, but there's still work to be done. We need to improve the model, but I think we're probably quite close to that now, a couple of weeks away. And that's it, really.